Hello and welcome to Talk Julia. My name is David Amos.
And my name is Randy Davila.
So Randy, this episode we wanted to take some time and I guess kind of talk a little bit about ourselves a little bit, but also some of the research and work that you're doing in graph theory using Julia. Well, I guess even beyond graph theory. At this point, we'll talk about that later. But why don't you start us off by telling us a little bit, maybe some of the backstory about you're working on this automated conjecturing program, which you've been doing in Julia now.
Right. For the listeners that aren't mathematicians, conjectures are open questions in mathematics for which you do not know the answer to immediately. Right. So famous conjectures would be like x to the power n plus y to the power n does not equal z to the power n, and these are integers n, and like there's no integer solutions to this. Like it was Fermat's last theorem, but it was a conjecture. Right. It was open for a very long time.
Yeah.
Or there's like Goldbach's conjecture, the twin primes conjecture. There's these open questions in mathematics that kind of drive new research.
And the whole like P versus NP thing.
Right, for complexity theory, right. So conjectures are like a fundamental building block of mathematics. Before there are theorems, there must be conjectures.
Yeah.
Right. So David and I had the privilege of going to undergrad together at the University of Houston downtown. And one of the professors there was named Ermelinda Della Vigna. She had a program called graffiti.pc, which was inspired by a program called Graffiti, written by Simeon Feitlowicz at the University of Houston. So she was a PhD student of Simeon's. And Simeon was a very creative mathematician.
Yeah.
And was the first person to the first person to actually write a computer program that would automatically generate conjectures, meaningful conjectures, not just simple statements like if n is even, then n squared is even, not things like that. The types of conjectures or postulates that Graffiti made were, I would consider, research conjectures, and they were research conjectures. Mathematicians like Paul Erdős and Fan Chung, like famous graph theorists and discrete mathematicians, worked on these problems and wrote papers on the conjectures of Graffiti. So Ermelinda Della Vigna at UHD talked about this, right? Along with Ryan Pepper, who was also my undergrad advisor, right? And a friend of both David and I.
Yeah, as an undergraduate, Dr. Della Vigna was my, this wasn't the title we used at the school, but like senior thesis advisor. I wrote like a long thesis for my senior project. That's what we called it at University of Houston downtown, and worked really closely with Ermelinda. And the whole project was working on conjectures from her program. So I would go meet with her in her office, and she would have printouts of the output from her program, and we would go through it and decide which conjectures we thought were interesting and what we would start to tackle and those kinds of things. And it was a really interesting experience. It was the first time I'd ever worked with an automated conjecturing program. It was also kind of my first real exposure to research style mathematics as well, right?
Like these questions that the program posed that you were working on, Dr. Della Vigna, she didn't know the answer to them either, right?
For the most part, yeah. Occasionally we'd come across one and she would be like, oh, that's actually known. You know, she knew about it from maybe some literature. Someone else had already had that, but that was actually pretty rare. But also, you know, she didn't know what the output was going to be. So it was kind of like this, like Christmas morning kind of feeling each time going in, getting this new thing. It's like, who knows what we're going to get? Like, we're going to get some really, really good stuff. But it was just fascinating to me that, you know, at the time, and really to this day, I don't really know exactly internally how her program worked, graffiti.pc, which I think the .pc stands for parallel computing. Do you know? Is that correct?
I did not know, but I can ask her tomorrow.
Because I think that was like one of the major improvements she made to Graffiti. So Simeon Feitlowicz was her PhD advisor, and she worked on, I think it was writing graffiti.pc.
Yes.
Was part of her
she
PhD.
Wrote, right.
Yeah. I'm pretty sure that was like one of the big improvements. And again, you have to remember this was like what, like the late 80s or early 90s that
Right.
she's
So
doing this? Yeah.
graffiti written by Simeon Failowicz was written in the late 80s.
Yeah.
I think it was originally written in Java, like
I
that.
don't think it would have been Java if it was the
No.
80s. I don't know what he wrote it in. If I had to guess,
Well, I know
it would
there
be
was
like
a version
C.
there was a version in Java eventually, but yeah. So just so the listeners like know, like when we say conjecture, we mean like a conditional statement. Like if object satisfies this, then something has to happen.
Yeah.
And these are the types of questions that mathematicians deal with. And the programs that exist, like Graffiti, Graffiti.pc, there's another one called Conjecturing, and there's another one called AGX by Linnet. So like Larson's Conjecturing, Linnet's AGX, I'm pretty sure, and several others. These programs generate these types of conditional statements, these open problems, or hopefully open problems, hopefully interesting problems. That's the goal, right?
Yeah.
They have generated them on like networks, like graph theory objects, graphs, as well as matrices, chemical graphs, number theory. And I even heard, I don't know if this is true, but I heard that a variant of graffiti early on conjectured F equals ma, like force equals mass times acceleration, based off of
That's funny.
based off of data, which actually leads me to I should just say it, that this is like a data science problem. Right, you have computed values on mathematical objects, and you're searching for relationships in all of that data.
Yeah, that's a good point. Yeah, it is very much a data science problem.
And the people that do it in the past did not call themselves data scientists; they were just mathematicians.
Yeah.
And they inspired me, right? So now I should probably start talking about like my contributions a little bit. So it's actually interesting that knowing about these programs and thinking they were really cool, because I was a graph theorist as a grad student, and I wasn't a programmer. I didn't know how to program anything, but I just knew about them and I thought it was the coolest thing. So I started to teach myself to program with the hope of one day being able to write a program like Graffiti and Graffiti.pc. That was like my goal, right?
Yeah.
And I started with C++ because that's what I thought I should use, and then a student told me that why am I not using Python? So then I moved to Python. Python 2 was like like that so long ago, it feels like.
Yeah.
I was sort of in isolation when writing this, right? Like when I was trying to figure it out, I wasn't talking to Simeon, I wasn't talking to Armelinda. I was on my own working on my PhD with Michael Henning in graph theory, but also at the same time trying my hardest to figure out how to get this thing to work. Like how to get a program to do this. And every little accomplishment felt so like big to me. Like just learning the appropriate way to like store the data and like read in the data. Building a database of objects to compute on, right? Like I'm a graph theorist, so I had to like in the early days, I literally like drew by hand like the adjacency list and like made sure that like I could store the graphs as like text files like on my computer. And I drew out like 100 of them, and that was what I used for my very first versions of the program, which I called TX Graffiti back then. So the TX comes from Texas State University, where I was working while I was also pursuing my PhD. But like I wrote it at TX at Texas State, and I was paying homage to Graffiti and Graffiti.pc with the name TX Graffiti. And this program actually turned out to be really beneficial to me. And led to a myriad of papers. I don't know how many publications it's helped me with, but I figured out how to do it, and it basically was just it taught me how to program.
Yeah.
Really, like learning how to get a computer to behave like I was behaving as a mathematician, because for whatever reason early on I was really good at asking questions in mathematics, like asking new questions. So I was just trying to figure out like, okay, so how do I do this? I look at examples. So I draw out examples and I calculate things, and I'm looking for patterns. How do I find the patterns? I have to do a bunch of examples and what patterns am I looking for? And like trying to figure out how to get a computer to automate that on my own without any help is what really taught me to program. And like I learned about like pickling data and things like that. So now So if you can't tell, I'm very proud of this accomplishment. I wish that I would have written a paper about it at some point. It just appears as one line at the end of my dissertation, like literally the very last few lines of my dissertation say many of the problems in this thesis were inspired or generated by this program TX Graffiti.
Yeah.
So what I wanted to do for the Julia community was to provide a general purpose conjecturing program for mathematicians that use like Julia. And honestly, it's faster than the Python version now that I have it written.
Yeah.
So I have it ready now.
Well,
I
and
did change.
before we get into that, actually, I do want to mention writing this program, gave you a ton of material to work on for your PhD. And that, and these were like genuinely interesting problems that it was generating. I mean, your PhD thesis was essentially like a collection of a whole bunch of papers that you had written
Yeah.
with your advisor, and these all had been accepted in like major journals and mathematics journals. So not only were they interesting problems to you, they were interesting problems to other people that looked at them, and I think have spawned other questions as well. Like you've had, those are getting cited, and work is being continued on that.
Right. There's a few problems that like people have written like several papers on. Like there's still open problems from TX Graffiti. There's one in particular that I worked on for years. I proved a partial result for it. Some mathematicians in Australia also worked on it. Like there's still like I wouldn't call them famous, but like well known or notorious problems that my program generated, at least like in my small graph theory community.
And then also doing this gave you and I the opportunity to actually work closely together. I didn't work on many of the conjectures or things with you, but you needed a way to compute a bunch. You needed to get the data. You got data for graphs, right? The graph representations that you could use to read in. But now you need, okay, I need a whole bunch of data, because these conjectures are basically establishing or proposing relationships between various properties of these graphs, these mathematical objects. And I guess we should be clear about what we mean by a graph. Not that we're going to be talking about graphs a whole lot, but not like a plot or something like that. But we're talking about graphs like a network, so nodes and edges, joining those nodes together, establishing these relationships between nodes. And I remember you asking me lots of questions. We had tons of conversations back then about, how would you compute this, and do you know of an algorithm that can do this, and we spent a lot of time thinking about how to compute these various properties, and we ended up writing a Python package together called GrinPy, which stands for Graph Invariance in Python. And I think what was the coolest part of that project that you and I did was that we started with a lot of like almost brute force kind of algorithms for some of these things, or like doing some research and seeing like, does someone know of a better algorithm, or I knew of a few algorithms that I had gotten to see as an undergraduate from Graffiti PC. There were a couple of things that I got out of that, and we were able to kind of reuse some of those and rewrite them in Python, because Graffiti PC was written in C++. But then you introduced me to the idea of using integer linear programming to solve some of this stuff. So a lot of what GrinPy turned into is using linear integer programming and these like optimization techniques to like rewrite these concepts, like these properties, as optimization problems, and use we ended up using the pulp package in Python to solve for a lot of that. So that was a really cool concept that I guess I hadn't really thought about, and we ended up. I mean, I think the vast majority of the graph invariants that are calculated in GrimPy are using that, and and it's so much faster than a lot of the other algorithms that we had.
Right. And just to let our listeners know that many of the things that we're concerned about, like conjectures on graphs in particular, graph theory, like graphs, the conjectures that are interesting to me as like an extremal graph theorist in a sense are the
Mhm.
conjectures that relate NP complete decision problem type functions to each other. So on graphs, there's lots of things that you can calculate that are NP hard to compute, which means basically if the graph is large enough, you won't be able to compute it. They're functions that there's no known algorithm that's going to give you the answer in a polynomial number of steps with relation to the input size being the number of nodes in the graph, right? So using these optimization techniques, the Python package that David and I developed actually can compute them on graphs like of relatively big size to me. Like I've computed some of these things on like 150 vertex graphs where if you weren't using something like a linear integer solver to do that, it would take a very, very long time.
Yeah. And so that's something, and of course, like your TX graffiti that wasn't really a part of TX graffiti. It was sort of like an extra component you needed, because really all TX graffiti needed was a data set.
Right.
And so you needed to produce the data set. And so we wrote that to produce the data set. And then that kind of has become its own thing that I've seen other people have been using it in projects as well, for different things, which is kind of neat. And that's something that maybe in another episode in the future we can talk about that. And I'd like to rewrite that in Julia.
Right. And I've started to a little bit, but because like I already have a data set generated from, I've just used the same data set, which actually leads me to why this new program that I wrote called Christy.jl is kind of different than TX graffiti and the other variants of. There's like a linear TX graffiti. Like the thing that I ended up writing in Julia over the past few weeks, or probably it's been like 5 weeks I've been working on it maybe. And I've gotten I was able to get it to produce conjectures almost immediately, but like customizing it and making it elegant and like simple to use and general for not just graph data, it took me a while to like kind of do. And like I had a realization several, like maybe 2 weeks ago now, that I was just kind of laying down and I was thinking about like how it would be nice to like write this like in a very like function approach, like a functional programming approach, opposed to how it is in Python, where like how TX graffiti is that I wrote in Python is it's not like users can like take that and use it on their own data. Like it's so specific to the data that I made. Right, so I wanted to bring to the Julia community a version of my conjecturing programs that I've written. And there's TX graffiti, linear TX graffiti. One of them was called that program.py. And I wanted to bring that to Julia, especially since I'm starting to really like fall in love with this programming language more. And because it's not an object-oriented programming language like Python, I was kind of nervous to kind of jump in and do it. I didn't know how hard it was going to be. And it turns out that writing a conjecturing program in Julia is very easy. It's a lot easier than I thought. In fact, the program that I ended up writing, which I call Christy.jl, consists of just 3 Julia scripts, so 2 modules and 1 script that kind of includes the functions from those modules. And this program, unlike my previous programs, has the ability to conjecture on any mathematical objects that you can compute invariant data on. So for our purposes, you can think of an invariant as a function that you pass in a mathematical object, and that function returns a number. Right? So if I look at the data that I'm using graph data right now. It's contained in a CSV file where the columns are like the invariants, the functions, and the rows are instances of graphs. So row 2 is a graph, row 3 is a graph, so forth and so on. So each column is an invariant, but then there's also Boolean columns, like which correspond to like is the object this type of object, or is it this type of object? So like graph objects, you can have like subclasses of them, like regular graphs, cubic graphs, bridgeless graphs, things like that. So there's also Boolean columns in here. And then I am requiring that there is exactly one column called name that stores the names of the objects in your data set, right? So, but really it's just invariants, Boolean columns, and then one column of the names of the things, right? Because the way that my program conjectures, it requires that you somehow have string names associated to the objects so that, it wants to conjecture very general questions to the user. So it wants to look at all the names for which the conjecture is true and try to find the largest subset for which a given inequality is being formed, which I should probably say, I don't think we've said yet, that my program conjectures inequalities between invariants. So you have objects.
Yeah.
So if objects satisfy some Boolean properties, then this invariant is less than or equal to some combination of another invariant or two other invariants or things like that. And currently, the way that I have the program set up, it's only going to produce linear inequalities. So invariant 1 is less than or equal to m times invariant 2 plus b, linear inequalities like that. And these linear inequalities that are found are going to be true on each instance of the mathematical objects in question. So, but if you didn't like linear inequalities, I happen to like them. Linear inequalities to me are the simplest looking, the most elegant to me. And a lot of things about this program I'm very proud of because it's elegant. It's the best version of the program that I've ever written, and that's why I kind of decided to change its name to kind of stand on its own in difference than my previous programs. So how does it make the linear inequalities on the data that you have? Well, I use jump. So in my core functions module inside of here, I make use of, data frames because I love data frames, but more specifically jump in the GLPK solver that you can use in conjunction with jump. So basically, what the program does is it reads in the data as a data frame, collects all the invariant names automatically, so it figures out which columns in your data correspond to numerical values. Those are assigned to the invariant names, so you don't have to provide it the names, you just have to make sure that they're along the columns in your data set. It finds the Boolean properties, if any, so those are the columns that are Boolean entries, just checks that it's the type Boolean array. So it finds these. But then to make the inequalities, it will read in the numerical values and select one invariant at a time. So a target is what I call it. And that target, it's going to try to form, for example, here, an upper bound on that target. And the way that it does that is by using a jump model in the GLPK optimizer. And it's going to find variables m and b, the slope and the intercept, right, for these linear inequalities. And it's going to minimize the sum of x times the slope plus b. So why would you want to minimize this sum? Well, we need to look at the constraints as well. If y is our target and we have x times m plus b is greater than or equal to y, and we want a really tight inequality, right? We want that inequality to be as close to equal as possible. Then that's why I decided to minimize this, right? So for minimizing this target function subject to x times m plus b greater than or equal to y, which is the target, minimizing that will give you a line that is kind of bounding this invariant from above by whatever that slope is and whatever that b is that it finds times the other values in the data set that you're going against, right? And there's other constraints that I had to play with to kind of figure out the best way to do this, and that's going to be some ongoing research on my part to kind of set what I would call hyperparameters of this optimization model, where I have that the intercept is no more than 1, the slope is no more than 2, the slope is greater than 0.25. These types of things are kind of arbitrary and really should be studied, should be tweaked by the user depending on their data set that they provide. But by the way, again, this is just a CSV file of data, right? So if you have your own CSV file of computable data and it's and the values are relatively close to the values in my data set, they're just, you have integer values, some floating point values, Boolean values, and the values are kind of close together, right? I found that when there was a column of data where the numbers are 7 times more than all the other ones, then that will break this this optimization model by jump will not converge. Right? There's like a problem that will happen. So you can do that for upper bounds, and for lower bounds, you want to maximize this linear sum, right? So if you're trying to target, like make a conjecture against target y, you want to maximize x times n plus b, right? Which is less than or equal to y. And I am astonished at how fast it does this, right? So when it forms these linear inequalities that are true on all of the data set, on all the data that you have in your data set, it's solving like there's a lot of constraints, but this is linear programming that can be solved quickly. However, but I'm doing this when I call my main functions, which I'll talk about in a moment. I'm doing that on like all the invariants like in my data set. And there's a bunch of columns. I forget how many columns I have, but there's a bunch of them. And it's just like, it's really cool to see jump work so well. And in like the API for using jump, I can't talk highly enough about how awesome these at constraint macros are and at variable macros are. And also jump version 1.0 just came out, didn't it? I think I saw that somewhere.
It did, yeah.
So that's awesome.
They just hit 1.0.
Jump is probably one of my favorite packages in Julia for sure. So then,
yeah, it's really nice.
So then after I use jump to create a bunch of linear inequalities on a given invariant, like trying to like find these possible questions to pose, you'll end up with like hundreds or maybe thousands of, or tens of thousands of possible conjectures if you like have enough data and enough invariants that you're looking at in your data set. So then you have to somehow filter them. This is one of the most difficult things in automated conjecturing, is filtering all of the things that the program will find. There's so many conjectures, inequalities that a computer can find, or a program can find on a data set between invariants on a given mathematical object.
Yeah.
But which ones are important, right? Like which ones like mean the most? And the way that I kind of solved this on my own when I was like, again, this program is very special to me in the sense that I had to figure out how to do this all on my own. And I was too busy working on like my dissertation to like read all the literature that what people have done in the past. So I kind of figured that, okay, so if I'm looking at inequalities and I want them to be strong inequalities, they should be tight. They should be equal a lot in the data set. And that terminology I did take from, I think, Shimian Feitlowicz's program that is called the touch number. So the touch number is how many times does the inequality that you find actually equal, not just less than or equal, but equal, how many times does that occur in the data set? So if it equals a lot, that means it's a tight inequality, and I want to push those to the top of the list for the user to look at, because those are going to be stronger. You want to always consider the strongest possible conjectures relating these NP complete, like invariant type problems, right? Like you want them to be close to each other. At least like as a mathematician, that's what I want. And then also, I try in this little line here where I get the expression of my conjecture, which, by the way, I have a custom conjecture type that I had to write, which I really like. Basically, so if the inequality between two conjectures is equal, and say conjecture 1, and the other one I'll call conjecture, and then conjecture 1, if the expression, the inequality is the same, I want to grab the conjecture with the most general family of graphs, right? So if the inequalities are the same in one conjecture where the hypothesis is like maybe this type of graph, and then there's another conjecture that has the same inequality, but their hypothesis contains all of those other graphs that I just mentioned, then I would just discard the prior one and keep the one with the more graphs in it. And that's why I require in the data set to have the names of the objects, the names of each instance of object, because I use those names to kind of filter through and find the one that has the most number of things that it's true for. Because this program it checks various types of hypotheses. It's not just like, if you have Boolean columns in your data set, it's going to check like, if it's this type, and then does this inequality hold? If it's this type, does this inequality hold? And you want the Boolean property with like the most graphs, and at the same time, the touch number, like the most number of equals. So it's like weighting those two things together. And that's kind of how I figured out how to do this a long time ago, and now I'm implementing it in Julia. So those are the core functions. There's a conjecture type that I had to write to like print the things out nicely for you to look at and stuff like that. But basically, with these two modules, and then the Christy.jl script here, which is also a module, we can make some conjectures. And there's two main functions right now you can consider when including Christy.jl, as long as you have that data set in your directory. Let's see. I'm going to first import into my Julia REPL my REPL, my favorite Julia REPL package. Hopefully you all know what that is. So it just highlights the syntax for you inside of the REPL. And then I'm going to include Christy.jl. So that's in my current working directory. And the first time you load these things, it takes a while because, again, I am inside of the scripts, I am importing data frames meta, jump, glpk. There's a lot of like packages behind the hood. Well, actually not a lot. There's like 5, I think, maybe, like CSV, data frames, whatever.
Yeah.
So then once you have like imported this Christy.jl script or module, there's two functions that you can use, and there's some hidden functions that if you go through the documentation, maybe you'll see, but I'm not going to talk about. Let's say, so, but the two main functions are, so they are, well, surprise me is probably the best one to start with. So if you look at the surprise me function, you don't have to pass anything into it. It's going to pick a random invariant from your data set that you have and then try to conjecture on that random invariant. So you don't even choose what it's looking at. It's just going to pick a random one. So that's why I call it. So it's like Christy.surprise-me. And the first time you run this, it is a little bit slow. But again, that will change after it runs this first time. And then it's like really, really fast to produce conjectures. So right now we're waiting. Christy's kind of sorting through all the possible inequalities, well, like finding them first using jump, and then sorting them by touch number, and then filtering them by generality. So it's like finding the strongest, and yet like the most, like, it sounds silly, but like they're linear, so they're like almost elegant looking to me. They're easy to read.
Right. Yeah. Yeah. And that's important because like there is sort of this aesthetic thing that mathematicians are really interested in. Like an ugly conjecture, even if it's true, I guess unless it's like super important for some deep reason, generally they'll kind of look at it and be like, I don't even know that I really want to work on that problem. Like, right? Like there's this idea of kind of a beautiful conjecture.
Like that was very important to me because I saw a lot of conjectures of some of the other programs out there, and they were so messy looking, I didn't even want to work on them.
Yeah.
Right? Like, so that's why these are so simple and like, to me, like beautiful. Like as a mathematician, I can look at like this first conjecture, I have no idea if this is true. If X is a connected graph and is at free, then the radius is greater than or equal to this Slater number. This is like a degree sequence type of thing. It's very strong. It hits 120
What
times.
What is at free?
Asteroid triple free. It's way too... It wouldn't be easy to describe, but it's like a thing that people study. And then we have this one's true. Radius is less than or equal to diameter. That's true. And like, but this is just interesting. Like, look at how simple these are to read. And if you're a graph theorist, then you would probably look at these and say like, some of these are interesting, right? Like, why is it saying that like if the graph is claw free and connected, then the radius is greater than or equal to the domination number? Like, I have no idea. It's probably false. Most of these are false. Most conjectures in general are false.
Yeah.
But like, it's happened to be the case that in my past, for whatever reason, the ways that I've formulated these things using like linear integer programming and almost like a machine learning technique, because it is sort of like, it's artificial intelligence, but it's almost using like machine learning ideas behind it. So that was the random one, but you can focus on an invariant if you want to. And that's with Christy dot write to me. So we're asking Christy to write to us, or write to me. And then you pass in the invariant that you want to look at. So maybe I'll look at the independence number. And I can limit the number of conjectures that I want it to spit out. So by default, it's 50, but you can set that to however many you want. So I'm going to say conjecture limbs. Maybe I'll do 1 to like 25 or something. So this is the write to me function, so Christy.write to me. And this is targeting a specific invariant that you're curious about. And you can see it's really quick, it's already done. spit out 25 conjectures. This first one is a famous result in graph theory that the independence number is greater than or equal to this thing called the residue.
Yeah.
There's been like 4 papers proving that in various ways.
Well, and it's actually really relevant to the history of all of this, because
yeah,
wasn't that the very first conjecture that Simeon Feitlovich's graffiti program?
I think that was the first major conjecture that like really got people's attention. What else? If G is so you have a connected graph and is a tree, then independence number greater than the total forcing number. I have no idea if that's true, even though I made this invariant up. So like the total forcing number is like, that's my invariant, I guess. I have more problem, like because of this program, like if you're a graph theorist, right, there's more problems generated by this program than you could ever like solve. Like a normal mathematician would have a hard time going through all of these. There's more things to work on than I can like ever work on, right? This is why I always collaborate with people, because I just see these things and like, that looks interesting, that looks interesting, that looks interesting. And then I just like start sending them out. So my goal with Christy.jl is to actually make this into like a package that people can go and install using the package manager maybe even. And then as long as you have a data set in your directory, a CSV file in your directory, it doesn't matter if it's graph data or not. As long as the numbers are relatively close together, generally speaking, and you have enough instances, this program will spit out conjectures on your mathematical objects. So like you could, for example, have matrix data where each like row of the CSV file corresponded to a matrix and the columns were like the trace or like eigenvalues or whatever, and just see what it spits out. Or a number theory, right? Like you could put like, or sequences even, like any type of data that you can calculate things on, this should work with. And I'd like Christy.jl to help like other like grad students out there have problems to work on, right? Just so long as they cite it.
Yeah.
And they don't say they came up with it on their own.
I think that's really cool, because just in the realm of mathematics, I could think of a ton of potential uses or potential areas that you could use this. One thing that I would actually be kind of curious to investigate is things like topological invariance. So they have some sort of like topological space, and that has many invariants associated with it, and people study these things. Geometric invariance even.
Oh, right. Yeah, that would be really
an
cool.
interesting thing. I do wonder if there's like, outside of mathematics, would this have interesting applications in chemistry or physics? Or
right.
My guess is it would. I don't know, but inequalities are useful for not just for like sort of these mathematical questions, but they have practical purposes as well. Like knowing like inequalities have real world uses that mean things to help you make decisions about things. So
right, like in this could be like, think about like maybe even like medical data where like each instance is like a patient and the columns are like blood pressure, age, or something like that. This would also conjecture on like relating those things. I don't know what it would say, but like it's feasible that it would do that because it's a very general idea. And I wanted to mention briefly though that some listeners might be bored with the linear inequality things, right? However, you can square entries in the data. Like if you had a column, you could have like this invariant squared, right? Or one column could be like this invariant plus another invariant, right? And then you'd get linear combinations of that, which would imply more complicated expressions on the right-hand side. So instead of like algebraically manipulating the solver to find the inequalities, linear is like, you can extend that by just making new columns of the other combinations you want. Just make, like I said, like a column summing two invariants or squaring it or taking the log or something like that. And I don't know, I'm really excited and I'm really proud of this version. And I hope that maybe I get some help because I've been working on it by myself for so long. It's like,
do you have this on GitHub yet?
Not yet. I have not put it up yet, but I will.
Okay. So yeah, I mean, it's really cool, and I could see it's still sort of in this like kind of basic form. So I could see like there's lots of room for this to kind of grow and expand and address other people's needs,
Right.
even more. But I think, one application of this that we kind of hinted at when we started the talk, but we haven't discussed a whole lot is just in education, because that was, like I said, my experience with Dr. De La Vigna as an undergraduate. I spent hours. I mean, I don't know how many hours, like dozens, if not over 100 or hundreds. I didn't keep track of it, of hours. Sifting through this stuff, and she would give me the list of conjectures, and I would go through, and we would, I would work on these things. So for example, you mentioned a lot of these conjectures are false, and that's true. But if you're teaching, like, say in this case, speaking to graph theory, if you're teaching like a graph theory course, then you want students to develop a sense of, how do you prove that a conjecture is false? How do you come up with a counterexample? How do you approach a conjecture? And so having a bunch of false conjectures is very useful in that case, right? Because they're a teaching tool. So I see that also as kind of a big application of this. Is here's a way to just generate a bunch of problems for students to.
Right. Like this would be perfect for like a summer, like an REU, like a summer undergrad
Right.
research type
Yeah.
of thing, because like there's a good portion of these that are accessible and also publishable to like undergrads. Not like
Hmm.
some of them, like I've sent some of these problems to like really strong mathematicians, and they're still open, and like people have worked on it. But some of
Oh,
them are
sure.
like accessible for sure. I really need to write a paper about this Julia program, and work on some of these problems, and um, kind of spread the word about Christy.jl so that like other mathematicians use it and get excited about discovering new math.
Yeah, and it'd be great to put it in a form where if they wanted to, they'd be able to just use it themselves easily. And I remember having discussions like that with the Python version of this, where you had come to me asking, could we sort of package this up where, we could send it to somebody, they'd be able to use this. And certainly that would be possible. And I mean, we never got around to it. And I don't know if you did anything like that. But one of the things that's so cool about Julia is that really you don't need to write like an interactive program, even to, like, they just need to install Julia and learn a little bit about using the REPL and they'd be
Yeah,
able to use
exactly,
this. So you kind of
exactly.
get the whole like interactive thing for free, and we don't even really need to like package it up as its own like app,
Right.
or something
Yeah,
that they.
like
I mean, certainly you could do that if you wanted to, but I think that's one of the coolest things about Julia is the REPL is so powerful and so intuitive that it kind of serves as its own little like mini application
yeah,
for
it
these kinds of
does.
things. So
It
yeah,
really does. Now that you say it out loud, it does.
yeah, definitely. Any final thoughts before we sign off?
I'm very proud of this pack of what will be a package. It's not a package yet, but it's very close. Um, and I think this is the first automated conjecturing program written in Julia. I'm almost positive of it.
Awesome. All right. Well, Randy, thanks so much for hanging out and talking Julia with me.
Yeah, it's been fun.
All right. Take care.